Well, we all know and love Pythagorean's theorem, a squared plus b squared equals c squared, and today we are actually going to use a bit of geometry and algebra to help us prove this. So there are many different proofs of the Pythagorean theorem, and this is one based on similar triangles, just like we've been working with for a while here. So we're going to do this. I'll do it with you so you can see exactly what's going on. If you need to pause the video and slow things down to see exactly what happened, feel free to do so. I'm just going to blaze right through these steps. So step 1, cut a 4x6 index card along one of its diagonals to form two congruent right triangles. Alrighty, they don't exactly make 4" by 6" note card. So I'm going to go ahead and make one myself and show you how you could make one as well. So in front of me I have a piece of paper right here, just an 8.5 by 11. And I'm going to go ahead and I'm going to measure 4" by 6". All right, so I'm going to do that and then I'll cut it out here.
So here is a 4" mark. And I'm going to just cut, or look right along there. For a 6" mark. There we go. Now I'm just going to connect those up. Make sure this is 4" up here too, about, ooh, I was close. Now I'm going to draw some lines. And this is where I'll cut. Right along here. Make sure that's 6" too, I suppose. Ooh, I got a little wonky. Gonna make an edit. Cut along that line, how about that? Alright, so then I will cut this 4x6 apart, and we'll move on to the next step.
All right, now that I have that all settled, I'm going to actually do step 1 here. Draw the diagonal and cut along it. So there's, oh, welcome to school. There you go. Here's the diagonal, and I'll cut right along that diagonal as well. Step 2, in each right triangle, draw an altitude from the right angle vertex to the hypotenuse. Okay, step 2 says to draw an altitude from the vertex to the opposite side, the hypotenuse of each of the triangles. So I'm actually going to do that right now by using my compass to find the altitude, which the altitude has to be perpendicular to the hypotenuse here. So I'm going to just look at the shortest distance from the vertex to the hypotenuse. It's a nice little shortcut for finding the altitude. So I see that the shortest distance is right about there. So I'm going to mark that, and that will be my altitude when I draw that in. And I'm going to do the same thing over here. It should be potentially really close to the same distance. So I've got my compass right on the vertex there. Shortest distance looks like is right about there. So I've got my notches marked there, so I'm going to use my ruler. And I will connect the vertex to those points. Here we go. Altitude for one of them. And altitude for another. There we go. Step 3, label each triangle as shown in the following diagram. Flip each triangle over and label the matching sides and angles with the same names on the back as on the front. All right, now it said to label both of the triangles just like they were labeled in the diagram there. So I will label C, C. This is A, this one B. Then I have X of C here. And I have Y of C because the hypotenuse is always listed as C. So here you go, you can see all those labeled. Now I'm gonna go ahead and just do that on both sides of every triangle. Oh, I need to not forget my other angles here, so B and A. There we go. So I'm gonna do that to this triangle, and then I'm going to do it on the reverse sides of each as well. Step 4, cut one of the right triangles along the altitude to form two smaller right triangles. So you should have a total of 3 right triangles at this point. All right, here are my 2 labeled triangles, just so you can see. I also drew altitudes on both sides. There we go. So I've got all sides of my triangles labeled. And now I can move on to step number 4, which is cutting one of the triangles along the altitude. Okay, so I'm just going to pick one and I'm going to snip it. Step 5. Arrange the 3 triangles in a way that convinces you that all 3 right angles are similar. You may need to reflect and or rotate one or more of the triangles to form this arrangement. Now, step 5 says to arrange the triangles in a way that makes me believe that they're all similar. Right now, I have a lot of differently oriented triangles, all right triangles, but they don't look similar. So I'm going to try to figure out a way that makes them look similar to me. So I'm actually going to flip this one over because now, see, these 2 triangles match each other, right? They're different sizes. They kind of look the same right now, but they are in fact different sizes. See, one's bigger than the other. And then this third one I'm going to arrange as well. Now all my right angles are on the bottom here, like this. Woo. And all my hypotenuses are up here. All right, so that helps me see, you know what? Yeah, they are actually similar. Even though they're different vertexes, C, A, they're all a little different, but they are similar. Step 6. Write proportionality statements to represent relationships between the labeled sides of the triangles. All right, so now I'm tasked with coming up with a couple of proportions, okay? So I'm going to break it down into just 2 triangles first, and I'm going to save my 3rd triangle. But I'm going to look at this larger triangle, see how it has this hypotenuse here. The whole thing is actually just called C, even though we have y of C and x of C, so it's split up into 2 parts. But I'm going to say that C over B is equal to the corresponding parts up here, B over Y. So I'm going to go ahead and write that out. So I have C over B is equal to B over Y. Now I'm doing this specifically, noticing that in the prompt they were asking me to come up with some proportions that include x and y. So right now I've come up with a proportion that includes y. So now I'm going to come to my 3rd smaller triangle here, and I'm going to look at this x portion here, okay? So I have x as well. And I'm actually going to do this larger triangle again, and I'm going to relate it to the smallest triangle, all right? So I'm going to look at how actually C, this long side hypotenuse here, over A, this shorter leg here, is actually similar, or is equal to, excuse me, A over X, the hypotenuse over the shorter leg. So I'm going to go ahead and write that down here, and I have C over A is equal to A over X. So now I have 2 proportions. Yours might look a little different. If you don't have an X and a Y, I would just strongly recommend that you come up with a couple proportions that do have that. Step 7, solve one of your proportions for X and the other proportion for Y. And if you've written proportions that if you haven't written proportions that involve X and Y, study your set of triangles until you can do so. So just using this X here and this Y here. Now, step 7 requests that we actually solve these proportions for y and for x. So I'm going to go ahead and solve them. And the way that we solve proportions is we're going to go ahead and cross multiply. Some people call this the bow tie method. We're just going to call it cross multiplying. So I will have cy equals b squared. And on this side on the right, I will have cx equals a squared. Okay, but they requested that I solve for x and y specifically. So I will divide both sides by c, y equals b squared over c, and divide both sides by c, interestingly enough, and I will have x equals a squared over c. There you have it. And then step 8, work with the equations you wrote in step 7 until you can show algebraically that a squared plus b squared equals c squared. And remember that x plus y equals c. Step 8 requests that we use these equations that we found in step 7 to actually prove a squared plus b squared equals c squared. So we have some interesting information right now. And we're going to see if we can figure out what's going on. Because we solved for these for x and y, and that's all fine and good, but I actually like working with things that are in the numerator rather than the denominator. So we're going to actually go ahead and multiply both sides by c again on both of these. So those cancel off. All right, and we get cy equals b squared and cx equals a squared. Now, let's think about what we're really trying to accomplish here. We're trying to ultimately get here, a squared plus b squared equals c squared. Right now, we've got elements of that, like this a squared and this b squared, but we don't have the c squared. We just have c. So what I'm going to do is I'm actually going to relate these two to one another in a single equation by just simply adding them, because I want them to look like this. So I'm going to say a squared plus b squared. Now, what happens when I do that is if I say a squared plus b squared over here, I know what a squared and b squared actually equal, right? B squared equals cy. Oops. Cy, like that. And I know that a squared equals cx. So when I'm looking at this other side of the equation, I could really say a squared plus b squared is equal to cx plus cy. All right, so that gets us a step closer. It looks almost like this equation down here, but we still have those x's and y's on the right side of the equal sign. So what I'm going to do is, if both of these have a c in them, I can actually factor that c out, okay? So a squared plus b squared then equals c. It's kind of the reverse of distribution. It's exactly the reverse of distribution. Times x plus y. Because, you know, if I were to multiply c back in there, I would get cx plus cy. So this is just another way to write. This is another way to write this exact statement. Okay? Now, why does that help me here? Remember back to the problem before it said, remember that x plus y equals c. X plus y equals c. Now, if x plus y equals c, and we have x plus y right here, we can do one of the best things that math ever had. We can substitute, right? So instead of c times x plus y, we'll get a squared plus b squared equals c times c. Now, what's c times c? Good. I know you said it. C squared. Wonderful. And thus, we have used some geometry and some algebra to actually prove that a squared plus b squared does in fact equal c squared.